Hey everybody, it's me, a cat named Quack. I'll leave.
We'll start that with class today. Worked on that in the background. Was trying to get that. It's hard. I'm trying to get its mouth moving. It's not registering the. It's not registering everything. What's up, William? Good to see you there. You're too funny. Thank you so much. We'll start class with a cat named Quan. It's saying audio levels are too low. What is it doing? It's not registering the audio from this microphone on the puppet thing. Such a bummer. Microphone input. 2 seconds. I'm gonna see if, because it'd be better if it actually did it. And we'll do some chapter 14. Cat named Quant preferences. Ooh, might have found something. Ooh, here we go. 1, 2, 1, 2. Oh my gosh. Ready for this? It works now. Hey everybody, how you doing? It's me.
It's me, a cat named Quack. Everyone doing all right? Good to see you, Catherine. Good to see you, William. Cat named Quack out.
Okay. Got it working now. Yo! We'll start class with that today. That's from last class, a cat named Quant. So we got it working. There we go. I'm trying to see the different things. Yo, good to see you there. Cat named Quant. Let's get some chapter 14 up and going. But I just figured out how to fix that. I'm using Adobe Character Creator and very crudely threw in our cat named Quant. And so we'll start class with that. But now actually we have its mouth moving. So it can actually do a little bit of talking here. I'm trying to or I'll show you on the main screen. You'll see, because you're like, Brian, what are you doing? So here, let me remove myself, and you'll see it on the main screen here. Oh, wrong button. So there is the character creator, and it's registering me. I had to grab another camera. So I was testing open mouth, closed mouth. I should have done a closed mouth on it. But yeah, so it can do the talking right here. But there's more you can do with this. There's this is as crude as it gets. So if I move around a little bit, it goes back and forth. And I tried to rig up its neck, but yeah, so that's how it's doing it right there. The magic behind it. Oh, buttons. What am I? Just clicking every button. All right, here we'll get serious here. I know it's scary, right? It'll be fun here to start class with that and see what people say. I forgot my AirPods today. So now I'm AirPod-less. I don't get to hear all the fun stuff going on. Chapter 14, which one? Are we going to do Chapter 14 homework? Oh, question number 4 on the homework. Cool, let's start with that. Thank you, Catherine, right there. So it's funny, I'm just seeing cat named Quant down here. I like up here, is that from last class? You bet it's from last class. Cat named Quant. I was just like, what if it was an animation? That is the only one I don't have on. Oh, nice job, Chapter 14. Bailey's excited about that. We are 6 minutes in. We're going to get serious right here. Number 4, is it the waiter waitress? What is it? What is it? It's got to be a hard one, right? It's the waiter waitress. The waiter waitress. Okay. We can do this. We got this. Okay. Let me pull it back up. Let me put the timestamps. The waiter waitress problem. The infamous waiter waitress problem. Okay, no more fun. Time to be serious. Chapter 14 question. Okay, here we go. And I want to put this on the screen here. Sorry, I was trying so hard to get this working this morning that I got behind on my stuff. 9:03, Chapter 14 homework. 14 homework. Question 4. Waiter slash waitress. Let's do it. Here we go. Okay, so for this problem right here, this is the sampling distribution of the sample mean. So we have to think about what's going on with it and how we solve it. So the first thing you do, who can explain to us the first thing you do whenever you get to one of these problems? what do you do? So write this down and remember this when you get to the test. So when you're doing the test, I want you to think about these steps right here. So you're out on the test, you get a problem like this, notation. Notation right here, mark your notation. So I need your help in marking the notation. Great job, Jennifer, right there, and Catherine and William. So I need your help marking all this notation. I see this right here, I see this right here, I see this right here, I see this right here. And then this right here. Lots and lots of stuff. Anything that we can mark right now in the problem. Let's see here, mu and sigma, great job. And did I miss the 50? Yours might be different, great job right there. We got to throw some points right there. We'll throw some bigger points later on. But mu, sigma, and n right there, you probably have. So this is going to be the mean, which is mu. This is going to be sigma, which is true standard deviation. That's going to be sample size, which is 30. And then this is earn at least, that would be the sum of the y variable of interest. Here, I'll disappear for a moment. Yeah, no worries, no worries. The sum of the y variable equals 350. Like the sum of her tips. And then this would read right here, the probability of, or I guess the best, or be the 90th percentile. So this is the 90th percentile. Why is it the 90th percentile? Because it's the top what percent? That's the 90th percentile, which would look like this on a distribution. It'd be over here on this side, because the 90th percentile is the what? So we've got a lot of things marked right here. A lot of things marked. Top 10%, great job, Cameron, right there. So tell me this, if we know 350 is the sum, then how would we get y bar, which is the mean? So what if we want to look at a mean tip, like how much you would have to get on average? So we know the sum of the tips is 350. Like how do you get the mean? Like the sample mean is found by taking the sum of the y variable and doing what? How would you find the sample mean? So the sample mean is found via what? You add up all, like, if you want to find the sample mean of height, you just add up everyone's height and you divide by how many people there are, divide by 30. So this is on average for 30 tables because we have the sum of the tips. And then we have right here, this would be 11.6 repeating right there. So that is what we get for the sample mean. So think about this. To make $350, she would have to average at least 11.666 repeating dollars to make that amount of money. But here's what we need to do. We need to draw the sampling distribution. The sampling distribution has the following formula. And let me make this very clear. Let's go to review 2. Now notice how we really haven't focused in on anything in the question yet. We haven't done really any of it yet. We've just marked all our notation. So if you've gone through and marked your notation here, you'll get to your formula sheet right here, which you should print off for the test. And when you look at the formula sheet, look down at the bottom for sampling distributions. Now, what you want to know when doing this problem is, are we doing a cat or a quantitative variable? Not a cat named Quant today. He's over there somewhere else. So are we doing categorical or quantitative? So look at all the notation on the screen, and you're right, we're doing quantitative. If we're doing proportions, you would have found things like P, P and Q. Those are going to be hallmarks of it. But we found things like mu and sigma. Now, be careful because a lot of people get confused because there's mu p hat and mu y bar. That stands for the expected mean, or the expected sample proportion, the expected sample mean, and the standard deviation of the sample proportion and the standard deviation of the sample mean. But those are just phrases. They're not mu times. A lot of people think, wait, this is mu times p hat. No. It's a full phrase, the expected sample proportion, or the mean of the distribution of the sample proportion. And then we have z-scores for both of them. But notice how these formulas are based on, did you find a mu and a sigma, or did you find a p and a q? And notice how we're doing the average tip. So average tip is quantitative versus like, is someone an in-state or out-of-state student? So now we want to go down here. Now that we know we're not using this top line, we're going to go ahead and find the mean for the distribution of the sample mean. And what is that going to be? For my problem right here, the mean for the distribution of the sample mean is equal to what? So look at my notation, and the mean for the distribution of the sample mean, or the expected sample mean, is what? The expected sample mean is what? What is the expected sample mean? Well, the formula says mu y bar equals mu. So what's it going to be? Mu y bar equals mu. 10.6. That's all. We just take literally that value, 10.6, and plug it right here. That's all it is. Now, once again, to repeat, if sample size increases, what happens to the mean? These are quick and easy questions on the test if you get it. If the sample size increases, what happens to the mean? Look at the formula. So the formula is mu y bar equals mu. So if the sample size increases, what happens to the mean? We know these things like that if we get them on the test. If the sample size increases, what happens to the mean? Nothing at all. So
It doesn't matter.
that it doesn't matter? I think it doesn't matter. So it stays the same. I'm going to get that to play through my ears too so I can hear my noises again. Next, we have the standard deviation of the sampling distribution of the sample mean, or kind of the variation in it, which is the formula right up here, sigma over square root of n. So I'm going to take the original sigma of a value of 4.70, and notice that it's going to get water because of the bigger n. The standard deviation is going to get water. So if we increase our sample size, standard deviation gets smaller, i.e. tighter, as n increases. And so that's what we get right there is a smaller standard deviation, which is part of the central limit theorem, that the distribution of the sample mean gets more normal, that's the other thing, and tighter as the sample size increases. So we take 30 right here and we square root it. We copy that and we go to 4.70 divided by square root of 30 and we get 0.858. Now I suggest keeping this in your calculator until the end because you might need those extra decimals. So I would not round or anything. I would just keep this in your calculator. Now, if this was a test question, we might ask you for the z-score of 11.6. Now notice 11.666 repeating and 10.6 have a difference of about what? Just pretend this is 11.6 and 10.6. Just pretend that right there. So 11.66 and 10.6 have a difference of about what? About 1. And think about this, the standard deviation is 0.858. So could you guess the z-score? Just give a guesstimate of it. So the formula for the z-score, and this is how it would be on the test, is observation minus mean over standard deviation. And yeah, that can be mu y bar over standard deviation. So it's going to be about what? So we have the observation of 11.666 repeating minus 10.6 over the standard deviation of the sampling distribution, which is this. And so we go over here and we solve the math. Notice how 11.666 repeating minus 10.6 is basically 1, then divide by the standard deviation, and it's a little bit bigger than 1, it's 1.24. Now with this right here, knowing that it's 1.24, I can actually get a very close guess to the answer. Let's look at this right here, then I'll get the exact answer. It's going to be very close to about, this is a hard guess. 4 decimals is super hard. If I had gotten that, I would have been super happy. So it's going to be very hard to guess this, but I'm pretty close to the answer, I believe. We have to go over here to the apps, which I'm going to pin right here. So go to this pinned thing. This is where you would not do this on the test because we don't have a way of you going to the apps. So we're going to go to this pinned message right here. On the test, you'd probably find the z-score, which we can always find. And here we go. So what I would do now is I would take the mean of 10.6, the standard deviation of that, and then I would find the probability above an observation. So we want to go above 11.666. And to 2 decimals, bam, 0.1069. I was less than what percent off? Let's look at my guess and look at this guess. I was less than what percent off? So my guess was 11.4, 11.3, but it was 10.7-ish, and I said 11.3. So if you look at how close I was with my knowledge of z-scores and how they work, I was like 0.5% to 1% off. How would we do this problem without a calculator? On the test, you would find the what? On the test, we would have you end this problem by finding the what? On the test, we would have you end this problem by finding the what? On the test, you wouldn't find the exact area, or you could do kind of a normal curve, and kind of draw it or talk about this being unusual or not. So on the test, you would find the z-score. Does that make sense? On the test, you would find the z-score, and then we could ask you theoretical questions about like the amount of probability because of the normal curve. So on the app, what do we have to enter in on the app? So let's look at the app again. You ready? So on the app, what do we enter in? On the app, you enter in the what up here at top. So start by entering in your what on the app. First thing you enter in is the void's a little further over today. I recalibrated the cameras. You're welcome, Sarah. Hope you got it. So on the app, you enter in the mean, and you enter in the standard deviation. And then you ask, make sure to click this button up here that changes it, find p-value using x, so we're finding the probability. Make sure you've clicked above because we're trying to find the probability that she gets more than this amount, and then graph above your answer right here. This is y bar, so that's your mean of the sampling distribution. That's your standard deviation of the sampling distribution. This is your y bar, and this is the area above. Does that make sense? How are we doing on that right there? I need to turn off autofocus. You gonna do that to me, camera? I did that between classes. Now I know where to go now. We did a lot of tech work yesterday. So, and then you'll get the answer here. Make sure to round to 4 decimals. You can just click the round to 4 decimals and you will get it right that way. Tougher question right there. The next part is not so bad either, but we've got all the information we need to solve it. The next question says the amount she earns on the best 10% of weekends. So think about this. This is near the best 10% of weekends. But the best 10% of weekends would be a little bit higher than this because this is the best 10.69% of weekends. Does it make sense when I say this is the best 10.69% of weekends? Does that make logical sense that this is the best 10.69% of weekends? So if this is 10.69, 10% would be a little to the right of it. Knowing that, if we're at 350 for the best 10.69%, I'm going to guess 352.80 cents. And we didn't get it right. I get one more guess. And we'll try this right here. It says to 2 decimals. And we didn't get it right. We're probably close. But now let's go back to the applet. On the applet, change from using p-value using x to find x using p-value. Now we're going to go here to 10% and make sure it's on the right side. But here's where people put in the wrong value. This is not how much money she makes on the best 10% of weekends. This is her what tip, because this is the sampling distribution of the sample mean. That is her what tip, because this is the sampling distribution of the sample mean. That is the what tip then on her best 10% of weekends. Listen carefully. This is the sampling distribution of the sample mean. So that value is her what tip. It's her average tip. Remember, she worked on, great job, Cameron, right there. It's her average tip. So we need to take this value and multiply it by how many tables she weighted. And there's the answer. So I should just put in 351. Probably, it's got to have a little give, right? It's got to. Oh, it does. It does have a little bit of a give. And so we got it right there. Really good question. One of my favorites. Really shows you know the concepts. If you can solve that question on your own and understand what you're doing, it's a very good question. And understanding what you're doing with the distributions. Should we start the quiz from the beginning and just finish these off? The rest aren't or the homework from the beginning, just do the whole homework as we usually do during office hours. What people would like, let me know. Or if you have another hard one, we could do that. Get that done. That's the waiter-waitress problem, the dreaded waiter-waitress problem. They switch between waiter and waitress. Waiter! Any more questions? Hey, Brian, do this one. I don't understand how to do it. We could just knock out the full homework right now. Should we do that? Get them all done? Whatever people want. It's your office hours, your choice. Yes, let's do it. Okay, let's do the full homework. Here we go. Okay, 21. Yeah. Thank you so much, my office hour crew right here. Homework question 1. Let's do it right here. The first question says, okay, so what do we do when we get a problem? Mark the what? Mark the what? We immediately start marking all of our what for 1,000 points in the chat. When you see a problem like this, start marking your notation. Know to know the notation. Know your notation. No, know your notation. Okay, I'm going to highlight these a little bit differently. And what do we have right here? Great job, William, on all those points. We got new levels. William's, I think he might even be at the highest level. People at office hours have the ridiculous levels. So we need to put in even more levels. Maybe I'll put 1.31 to end. So great job. Here we'll throw Sarah another 1,000 points so you can get a level up too. Just keep showing up and keep getting those points. We keep throwing them out right there. There you go. We went to roof level right there. So what is any of this notation? Any of it. On the test, you would sit down and you'd be like, okay, what is any of this notation right here? What is any of it? Any of that notation on the screen. I'm going to go grab this from over here. So you're looking at your formula sheet and you're like, okay, wait a minute, what do I do right here? How do I solve this? The mean, and you are correct, Lindsay, Sarah, oh my gosh, Sarah, mu, exactly, mu. So we're going to call this mu, which is the mean, and that is mu, not mu y bar, not mu p hat. It will be mu y bar, but right now that is just mu, and this is sigma, and then this can be here sample size of small, and this can be sample size of subscript medium. The subscript is just like denoting, it's still just lowercase n, but sample size, and notice I highlighted all the sample sizes in blue. Now, what do you notice about 2, 49, and 81? This question is kind of neat because it helps you out by making 2, 49, or 4, 4, 49, and 81 are all perfect whats. 4, 49, and 81 are all perfect whats. I'll start writing this out. We know now that we're using this information right here, because we have mu and sigma. Be very careful because there is standard deviations for other problems, but you have to say, is this a population standard deviation? What is it? Perfect squares. Cameron's dropping a square in the chat. I love it. And so what we do right here is we'd have for the small, so we have a small, medium, and large sampling distribution. So let's go right here and ask, what would be the mean for the small distribution? So we're making a grid right here where we would have the small, small, medium, large. And we have the mean, and we have the standard deviation. So what is the mean going to be for the small? So it's going to be mu y bar equals mu. So if mu y bar equals mu, that's the formula we're using right here, so we've got it right above it. We're just literally going to use this formula right here, plug it in. What would be the mean for the small? Well, it's mu y bar equals mu. So go look at this right here. Mu y bar equals mu. So you take mu, you plug it in because we're trying to find mu y bar. And mu y bar is equal to mu. So it's just 39. What's going to be the mean for the medium? What's going to be the mean for the medium? So the mean for the medium is 39. Because as the sample size changes, nothing happens to the mean. So the mean would stay the same. But what changes, remember the two things that happen according to the central limit theorem? It gets tighter and more normal. Well, tighter is the standard deviation being divided by the square root of n. So the distribution becomes tighter via larger n. So large enough n becomes normal enough. So we take the original standard deviation right here of, was it 4? I think it was 4, right? It is 4. There it is right there. Sigma is equal to 4. We take 4 and we divide by square root 4. We take 4, we divide by square root 49. We take 4, divide by square root 81. And this is equal to 2. This is 4/7, which is 14, 28, 42, 56, 57. At 0.57, we'll check our numbers right there. I think it's about that. And that is equal to 0.4444, repeating right there. Let me check my 4/7. I kind of know that one off the top of my head. It is. Good. And there we go. A seventh is a really interesting decimal because when you think about a seventh, it's actually 0.1428, which is part of like 1/7 right there. If you ever look at it, it actually is like 2 times 7, 4 times 7. So I always find the 1/7 a very interesting number. And then if you do times 2, it's the 28 becomes it. So times 2 is when it's 28, and then it would be 42 next. But I think at that point it would round up to 43. So if you do 3/7, it'd be 43 rounded up. But interesting stuff. I don't know. I like math. So decimals are neat. Ninths are interesting. 11ths, this is my last comment on this. 11ths are interesting because when you do 1/11th, it's 0.09090909090909. So it's 11ths are pretty weird. So how do you cram all that info into winter mini term? I don't know. Winter mini term it's fun. Winter mini term is fun stuff. You know what we just found? We found the mean of all these. It was 2. And the next one, the standard deviation was 0.57, right? That was that one. And then the last one is 0.444. Doesn't round up yet. And then which of these is going to be the most normal? Well, it becomes more normal when the sample size is what? Moira, good to see you here. Yeah, of course. Send it right now. Put it in the chat, and I'll tell people to do it, and I'll pin it. Come to class. I'll pin it both ways. And we'll do it for Moira. We can send out announcements or whatever you want to. So I can't imagine trying to learn all these chapters in a short amount of time. It helps to be like only focusing on one thing, because that's all you have. And then I tell people during winter mini term, like, this needs to be your focus. Like, don't be working a job. It's like you're just doing like 2 weeks, is it, or 3 weeks? I think it's 2 now. 2 weeks of like everyday class. And yeah, so let me post Moira's link right here. But yeah, I tell people during winter mini term, like, this is your job. It's very tough. It's like if you come every day and work every day, you're good. But if you're like, I'll take 2 days off, it's like taking a month off from school. You're putting, what's the hardest chapter to remember for exam 2? I'm taking it Monday, so I have less time. I'd say the hardest chapter, you're welcome, Moria. The hardest chapter is like chapter 7 and this chapter. The other ones are more memorization. These are very mathy. If you get them down, you get them down. If you don't know how to do them, you don't know how to do them. These are chapters you can't really guess, but when you know how to do them, it's like knowing that the sample size, when it's larger, is more normal. The palettes are the largest. So the palettes, because the sampling distribution of the sample mean approaches the normal as the sample size increases, and the underlying distribution doesn't matter. That is the central limit theorem right there. So literally, the central limit theorem in place right here is going to be this right here. And we know this, and I'll show this really quickly, but central limit theorem applet. Snap, you're welcome. So here's the central limit theorem applet, and the answer states regardless of the underlying distribution. So we have a distribution that looks like this right here, and there's a crazy one, and we only have a sample size of 5. Wow, central limit theorem made it normal automatically. Skew is one of the hardest things for it to deal with, so we're going to make it more skewed because skew is harder for it to deal with to normalize. Looks pretty normal, but if you go down to a smaller sample size, it's going to be more skewed, and as sample size increases, it becomes more normal, and that's what the central limit theorem states. So since the palettes have the largest sample size, regardless of the underlying distribution, whether it's skewed or not, the palettes will be the most normal. It doesn't mean they will be normal. They'll just be the most normal because as n increases, it becomes more normal according to the central limit theorem, which is a theorem, which means it's true, mathematically true. Okay, wait, we don't want to see the answers yet. Can't tell I really like these chapters. The sampling distribution, the sampling chapter, chapter 10, is one of the toughest ones because it's very subjective. Here we go with the next question. Let's practice and learn the concepts. And remember, we are here to learn the concepts. That's why you'll see me go into these extra parts of the questions to show off what we're learning. So stay tuned. A standardized test right here. Well, what are we going to do? Say it in the chat for 1,000 points because we've got a new question, which means we need to what? New question, time to what? You know what we're going to do to start any of these questions on the test? You get a question like this. You're going to go over here. You're immediately going to start writing down that notation, brother. Is it over here?
Notation,
that notation, brother? Did you guys just hear notation, brother? I don't know if you did or not. That's from Leo. Back in the day, Leo would say notation, brother. It might be that button. You did?
Notation, brother.
I memorized my soundboard. I just can't hear it. Notation, brother. He would always say that whenever we got to a question. He'd be like, notation, brother. Okay, so now that we got that, let's hop in here and start marking it. So we can get down, I'll mark it right here for us. It has a mean of this and a standard deviation of this. So the test is quantitative because it's what is your score. So that's a quantitative mean and that's a quantitative standard deviation. Notice the question is, what did you score on the test? So probably always start these questions, probably always, by identifying if we're doing proportions or means. But since we're doing a standardized test, we're obviously doing what? Proportions of scores or means of scores? Because we're looking at standardized test scores, and we have a mean for it, and we have a standard deviation. We're doing means, exactly. So now that we know we're doing means, we literally just found mu and sigma. And when you find this, you won't be finding this mu or that mu right there. You won't. That's not the mu you find. That's not what you're doing down there. Those are, once again, the phrases, the expected sample proportion and the expected sample mean. Those are not mu times p hat. That's a very common misconception. We just found that quantity right there, and we found that quantity right there. Next, we have two different sample sizes right here. We have a smaller class and a larger class, so we'll mark it smaller and larger. And once again, what we're going to do right here is we're going to do for the smaller class and for the larger class, let's go ahead and write down their what quantities. So we have a mean and we have a standard deviation. Ooh, totally made this wrong. Let me redo this a little bit right here. And we need to go here like this and put it like that and do our grid again. And here's where the mean will be. So this will be the mean right here. And this will be the standard deviation right there. So mean and standard deviation and small and large. So what is going to be the mean for the larger class? The mean for the larger class is mu y bar equals mu. So the mean for the larger class is mu y bar. So what is mu y bar? It's equal to mu. So the mean for the larger class is what? Now let's talk about what this means. The mean for the larger class is what? Mu y bar equals mu. It's 141. So just think about this theoretically. If I tell you the average UT student is 5'8", if you went out and talked to a student, how tall would you expect that student to be? Just random student on campus. How tall would you expect them to be? 5'8". But let's say I had you talk to 100 students, and I asked you what average height would you expect to see from the students? If you talk to 100 students, what average would you expect to see from 100 students? You expect to see, because if one student's 5'8", you'd expect the average of 100 students to be what? That's what mu y bar is, the average mean, or the typical mean. You'd still expect 5'8". Because one student's on average 5'8". If I talk to a whole bunch, they'll probably average to 5'8". So that's what we're finding right here. So the sample size doesn't matter. It's still that you just expect the average if you take a bunch of things and average them. And so with this right here, the large class is going to have 141 also as the mean. But what changes, as we keep saying, is the standard deviation. We have to take the standard deviation and divide by the square root of n. So the smaller class is 9, which is going to be 3, just solving the math for 9 over 3. The larger class is 25, so that's 9 over square root 25, which is 9 over 5, which is that right there, 1.8. Just make sure to solve your math and check your numbers. I'm doing it in my head. Please yell at me if I get it wrong. Or be nice, don't yell at me, but tell me if I get it wrong. So the question goes on to ask if things are unusual. So think about this. Which class has more variation in it? Which class has more variation in it? Variation would be measured by the standard deviation. So it would be a bigger spread to the class. Which one will have more variation in the scores? The smaller. Don't worry, William. We'll throw you 1,000 points right there, William. You haven't given them some out lately. The smaller class, because it has a larger standard deviation. William, 5,000 points. We love all answers here. We practice up. More variation is going to be the larger standard deviation. And so when you increase the sample size, the distribution gets water. So remember via the central limit theorem, if we go over here, how did we lose our central limit theorem? We lost our central limit theorem. As we increase the sample size, the distribution becomes tighter. So here's a sample size of 5. There's 25. So it becomes tighter. So as n increases, the distribution of the sample mean becomes more normal and tighter. And you see right there, 25, exactly. So 25 has a smaller standard deviation because it's a larger sample size, tighter distribution. Same mean though, so the mean is just the mean, mu y bar equals mu. And so now when we look at this, this question goes into, well, are these things unusual? And so both distributions will be approximately normal, and that's because the underlying distribution is normal. So the reason they are both normal is because the original data is normal. I do want to pause on this, and you should know how many conditions are there for the sampling distributions. Oh man, it's from a long time ago. How many conditions are there for the sampling distribution? How many conditions are there? How many conditions are there for each sampling distribution? There are how many conditions? There are 3 conditions. I'm trying to find it. I think I deleted the sheet with it. Oh my gosh. No. I think I got to write them down again then because I deleted it. I do have a cat named Quant over here. So let me go ahead and write them down. There we go. There's the cat named Quant over there. So the 3 conditions are, it opens up on the other screen. The 3 conditions are random, which means we randomly select the data, 10%, and then we what? 10% means less than 10% of the data is selected. And then we what when we do the first 2 conditions? We what when we do the first 2 conditions? Because we have a decision point now. Because we'll either go success failure or we'll go large enough n. We pause, put the pause in the chat. Because now, remember we said this is quantitative, check the variable type. So once you check the variable type, you say, oh, wait a minute, I'm doing means. So this is where we do large enough n. So this is large enough n, and this is success failure. If you did proportions, it would be success failures, which states we need at least 10 successes, at least 10 failures. If you're doing means, it's going to be large enough n, which states check the shape of the distribution to start. So check its shape, then know the sample size with the shape, and I'll write this down for you here. But we first check the shape, so large enough n for us. Large enough n. Lowercase n. And then step 1, check shape. And we really have normal, skewed, very skewed. And then we have step 2 is going to be sample size required. And it's either 1, 25, or 100. And then step 3 is your sample this or larger. Okay. Nice job right there. Check the variable type. Nice job, Sarah. Great notes in the chat. And if you look at this right here, our distribution is unimodal symmetric, so it's normal. So that means we need at least a sample size of 1, and that means you're fine because your sample sizes are 4 or 9 and 25, and you'll always have at least 1. So because of that, how you doing, Kat? Because of that, the distribution will be normal. And both distributions are approximately normal with a mean of this. The distribution is smaller, approximately normal. Distribution cannot be determined. That's fine right there. They'll be approximately normal with a mean of 141. Now we get into how unusual are these. And so with this right here, we can do it pretty quickly if we want. I'm thinking it through in my head. The smaller organization has a z-score of 3, and the larger one has a z-score. Oh, man. This one's hard to do in my head. Is it going to be, I think it's 5. I'll show how I did this. And the smaller one is more likely to have success. Did I do it right? I did. Okay, how in the world did I get this? Well, what is the notation of observing a mean of 150? So once again, the notation is going to come into play right here. Show you how I got this. So let's look at this. What is the notation of observing a mean of 150? What is the notation for observing a mean of 150? As in, what is 150 in notation? So if they saw a mean of 150 in the sample, boom, Sarah, you got it. This is Y bar. Be careful. So it is Y bar because it's not the truth. It's what if they saw that in a sample? Like, what is the probability of this sample? So great job, Sarah, right there. 5,000 points. Jaden, good to see you here. So that's usually where people get tripped up. And do you see y bar in one of the equations? Do you see it over here? Because now we can use y bar to find a z-score by taking the observed sample mean minus the true mean over the standard deviation, like the distance they are away, and standardize that, and that's the formula right over the shoulder right there, that one with the mean. So let's do that right here, and that's what I was doing, is I'm going to take the values, so we'll just remember y bar is 50 for this example, and we go down here and we just plug in the numbers where we have for the larger distribution, or the smaller first, 150 minus 141, difference of 9, and then we divide by 3, so 9 divided by 3 is 3, that's 9 over 3. And then for the other one, it's 150 over 141, and this is where I paused, and I was like, okay, can I do this math in my head? And apparently I could, because that is 5. Does that make sense right there? All we're doing is observation minus mean. Let me highlight it as I say it. Observation minus mean over standard deviation. Observation minus mean over the standard deviation for the larger. So this is the smaller, and this is the larger, and just figure out their distance, which is 9 for both, and then standardize that distance for the distribution respective to its standard deviation. And we get the z-scores. The next problem is virtually identical, and it just does a z-score that would be below. Be careful you don't put in the negative. How much below is this value right here? It's how much below 141. Just tell me 133 is how much below 141, and I'll show you what I'm doing in my head. So like if you can do these in your head, you're really ahead of the game. If you can write them down, you're doing great. It's 8 below, right? So then I think, what's 8 divided by 3? 8 divided by 3 is 2.66 standard deviations below. It'll round up to that. And then 8 divided by 1.8, oh my gosh. So it's 4 and 0.8 over 1/8. I can't do that one. I'm so close. It's close to 4.42. No! Okay, let's go find the answer. Why'd they have to use decimals? Okay, so let's go and take that difference of 8 right here. It's 131. You don't include the negative when you do it. So it's going to be 133 minus 141 over 3, which is 8 over 3. It is negative, but we will take the negative away when we do it because we're just going to say how many standard deviations below. This is still a difference of 8 right here, and over the 1.8. This one I was not able to do, but so negative 8 over 1.8. It's going to be very close to what I found, but not exactly. And so now we go here and do 8, not that. 8 over 1.8, and it's 4.4. Oh, I should have known that. Because it reduces to, yeah, 0.4. Oh, I could have figured that out with my knowledge of decimals. Should have done it if I did that. Oh, I was off by, no! I got to throw people points in the chat for solving it and getting it right. But we're just standardizing those differences. I was trying to do it the longer way in my head, but I didn't do it the theory way. 5,000 points, great answers right there. And we're just standardizing those differences. I wish it had you put in a negative z-score because they're below, but it does say in the answer standard deviations below. So it does clarify and tells you to do that they are below. Preferably, I would put in a negative z-score. A waiter believes. What do waiters believe these days? So 4 to 6, 23. Chapter 14, homework. Question 3. A waiter believes the distribution of tips has a mean of 9.6 with a standard deviation of 5.4. Explain why you cannot determine the probability that a given party will tip him at least 20. Choose the correct answer. Well, because the distribution is what? So he wants to know for one party. And we could do this. There's ways. It should say it's skewed, right? So there's actually ways to do this. You could just simulate it, and yeah, you could still do it, but you can't use the 68, 95, 99.7. So it should say, explain why we can't use the normal model to do this, and the answer is it's skewed. So the distribution is skewed, meaning it's not symmetric, and does not meet the condition for the normal models. That's probably going to be it. It's just not normal. Yeah. But it should say explain why you can't use the normal model. Can you estimate the probability that the next 4 parties So what condition is this getting into right here when it's like, well, could you do it for 4 parties? It's trying to see if what is what enough. It's like, it says slightly skewed, so doing large enough. It's like, this is a little bit of skew. So if there's a little bit of skew, and please note, because I think this one's going to be a little bit weird on it, if there's a little bit of skew, you're probably looking at an answer between 1 to 25. Because the more skewed it is, the larger it needs to be. These numbers below are the requirements, so we're probably at like 10 or 15 because it says slightly skewed. I would say no, a party of 4 is probably not large enough. That looks excellent for the central limit theorem to kick in. And now it jumps up to 10. This is where it gets iffy. While sample size of 10 parties may not be large enough, it is likely that the sample averages is starting to approach a normal. Okay, the standard deviation is going to be this. Divide the original one by square root of 10. That looks about right. Yeah, now we just need to check. The only differences between these answers look to be the standard deviations. And it does say the tip is is 1 standard deviation away above the mean. Let me check the new. It's probably square root of 10 is between a little more than 3. So the new standard deviation should be this right here. It's going to be that one. And what I'm doing is I'm taking 10 square root and dividing sigma by it. Once again, notation, and there it is. So if you knew the standard deviation, and then we could take right here this and do 15 minus 9.60 divided by, and there it is. It's a little more than 3, which confirms the answer. Are there any questions on that one right here? Because I kind of did that last part quickly because I knew the notation. I knew the sample size was 10, and it's like, well, it's approaching a normal because as n increases, it becomes more normal, large enough n condition. And then I took the original standard deviation of 5.40, divided it by the square root of the sample size, sigma over square root of n. The mean is still the mean, which is, does it say it on here? It doesn't say that. But then I found out how far away the mean was from 15, and then I divided that by the new standard deviation. Questions on this one? I kind of want to get the full thing done right here, because we've got, I think, 3 more questions. So I want to get the full thing done. Full homework done! What do we got right here? Which of the following is not needed to check the estimate? Well, we're doing means, so which one is not needed? Random, 10%, and then which one of these is not needed? Which one of these is not needed? Success, failure. The success, failure condition is only for categorical data, so remember that when you're doing your conditions. The success failure is for categorical data. We're not checking at least 10 successes, at least 10 failures. It's for categorical data. This one's pretty cool because it shows you what's going on with the central limit theorem. Now, when we think about theoretically what would happen, the mean always what's or is expected to always stay the same. So if we look up here at the notation of this, what would the mean be for all these answers? What would the mean be for all these answers? So if you look at this problem right here, and if we say, well, for a sample size of 20, 30, 40, so here's the mean. It's just going to be the same, right? So there's the mean, and there's the standard deviation. And then we know mu y bar equals mu. So we've solved all those. And then standard deviation of the sample mean is equal to sigma over square root of n. So now we need to find all the new standard deviations. So please slow me down. The easy part of this question is finding all the means. All we do is write down the mean and just copy paste it. We've done half of it. But the standard deviation, we need to take it and divide, and I wish they were perfect squares, but we need to take this standard deviation right here and divide it by the square root of all the sample sizes. So now we take, and thank you so much, Catherine and Sarah and Jennifer and William and Cameron and everyone for being here. We're going to take right here 30, square root it, and we take 19,568.05, divide by that. There's the first one. We'll worry about decimals, 2 decimals, so there we go. Then we take 50, square root, And then we go 19568.05 divided by, there's this one, 2 decimals. This is cool because all we need to do is move the decimal on this one. So we go 0.805, because all we're doing, and then 1956, all we're doing is moving the decimal, and that'll round up. Because square root of 100 is 10, so just move the decimal place over. Does that make sense? This one was the original standard deviation divided by the square root of 100. Square root of 100 is 10, so move the decimal over for that one. So that's easier. Isn't 100 square root of 200 like 14.4 or someth14? 14.414. I don't know. I can't divide can't divide this number right here by that. Got to carry decimals. Do not. You need to carry all your decimals on these questions. They will be kind of cranky if you don't. So don't have them cranky. Divide by the right numbers, because I do it wrong. There we go. Carry decimals. Solve, and we're good. There we go. So the thing is if you do a simulation, and then you look at what you see, so this is simulated values, look at the values. They all line up, because simulations will show what we should see in reality, so the theoretical means are reasonably close. They're not very different, they're not exact, so they're reasonably close to, and also these are reasonably close. What they're saying is the values you get over here for the mean, 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 the standard deviation are all reasonably close, and they are because the simulation shows what we do see in reality. Good question right there, just has you find a lot of standard deviations, and notice that the mean stays the same. The histogram to the right shows the compensation. We got to mark the question. 5423, chapter 14, homework quiz 7. Question. Did we miss one? I don't know how we did that. 251, chapter 14, one question. Okay, last question right here. What do you think we got to draw when it comes to this? How is that distribution skewed? Go back and meet your who. You got to talk to your what right here. Who do we got to talk to right now? Who we got to talk to? You know who that is right there.
It's the Monster Man.
So we got the Monster Man on the screen, right to the high, left to the low. I invested in a mini whiteboard, and it works wonders. Whoa, you have to, Cameron, send me what that looks like. We got some Monster Mans in the chat. Right skewed, right to the high, left to low, whatever way the Monster Man's tail goes. Explain how these histograms look as we increase the sample size. We'll take a look. They're becoming more normal, and do they look there? Question, you going to be crazy right here? You're saying that's super skewed? But I think they're saying that this is super duper skewed. So here's the thing. If it's normal, we only need a sample size of 1. If it's skewed, we need a sample size of 25. If it's very skewed, we need a sample size of 100. If it's super duper skewed, new terminology. Now if it's super duper skewed, if it's super duper skewed, then we need a sample size of like 500. Just the more skewed it is, the larger n needs to be. So super duper skewed is 500 right there. And it looks like we have a super duper skewed. Good to see you here, Emma. So the simulations support what the central limit theorem says. What the central limit theorem says about the sampling distribution of the sample mean, because as the sample size increases, the peak of the histogram stays about the same, because that's where the mean is. The shape of the distribution becomes more normal, and the variability in the sample means becomes smaller, so it decreases right there. Comment on a rule of thumb. Someone says 30 is always large enough. 30 is always large enough. There are in the Vol books in the student. Oh, really? Send me what it looks like. If you want to post it or send me a picture, I'd be interested in what it sees. That's pretty. Oh, yeah, you're talking. I know what you're talking about. I thought you meant like, yeah, there's good right there. Good to practice. 30 is not always. Yeah, invest in one. Good stuff. Since the distribution for the means. No. Yes. You need even larger sample sizes. Basically, someone's like, 30 is always a large enough n. what would you say to someone to end office hours? If someone said 30 is always large enough, you'd be like, well, it depends on what it is. If someone said 30 is always large enough, you'd be like, it's not a good rule of thumb. You're wrong. Why? Because 30 is large enough if it's skewed. 30 is large enough if it's normal. Because that's what they're saying. Someone says as a rule of thumb, depends on how skewed it is. Is it super duper skewed? Then you're talking 500 sample size probably. Is it super duper ridiculously insanely skewed? Maybe 1,000. Once again, we go by the numbers in class and on the test. We say skewed and very skewed, but there's things that are like ridiculously skewed. So the more skewed it is, not if it's highly or super duper skewed. Exactly. Then you need like 100 or 500 or 1,000 if it's super duper duper skewed. It's just like the more skewed it is, the larger it needs to be. And with that, we'll be back here with class. Get ready for a cat named Quant. Bye for now!